All right, at long last we get to here, area and Riemann sums. What's all this have to do with anything? Well, here's why the Riemann sums make sense. Or the other way around. This is why our intuition matches what the Riemann sums say. We have y equals f of x on this closed interval. Suppose we partition the interval. Again, we're using a regular partition, or as regular as my bad picture will make it. We choose a random value out of each of these subintervals. And then we form this expression, the Riemann sum, the sum as I goes from 1 to n of f of c sub I times delta x. Now, what does that mean? Well, here's how to represent this geometrically. F of c sub I, f of, in interval number 1, f of that is that height times delta x, that's this distance. Well, look, there's width, there's length. If we take that rectangle with that length, which is f of c sub I, and this width, which is delta x, that is the area of that rectangle, which we've been using all along. That's for I equals, this is subinterval number 1. When I equals 2, then we have subinterval number 2, and that would now be this height. And we have that rectangle, and we have that length times that width, and so on, and so on, and so on, and forming those heights. And what we have formed then is a collection of tall, slender rectangles. That, when we form this Riemann sum, what we are finding when we take length times width, and then number 2, length times width, then number 3, length times width, then number 4, length times width, and on and on and on until we get number n, length times width. We're finding each one of these is the area of one of these rectangles. Now here's why intuitively it makes sense. Suppose we want to find the area of the entire region under this smooth curve. Let's call that A. That's the area of the entire region. Well, the area of these rectangles is approximately the same. The area of the rectangles is, I brought my eraser. The area of these rectangles is approximately the same as the sum of those blue rectangles that we have over here. Why is it only approximation? Well, look, because we have this little leftover bit, and we have too much over here, and we have a little bit too much here and not enough here, and a little bit too much here and not enough here. It's only an approximation. The question is, how could we make this approximation better? Well, if we take a refinement of the partition, then let's just look at this little piece edge on, just this little piece of the picture. We have this purple curve coming down, right? And we have this blue rectangle and this red height that we were using. Right? And so we have this little leftover piece. But if we refine the partition, now we have more and more and more of these rectangles. And now these little leftover bits become smaller and smaller and smaller. And then we refine those, because now we could zoom in on this picture even more. It would look like this. Each one of these tiny ones would look like this if we magnified. But then we refine the partition again. And then more and more and more of these get used, and fewer and fewer. And so what happens is, as we get more and more of these rectangles here, more of this gets filled up. The approximation gets better. To make the approximation better, you refine this partition. What that means is n is getting larger. As n gets larger, the number of rectangles gets larger, they get thinner and thinner and thinner, and the approximation gets better and better and better. The question is, what can we do to make the approximation vanish? Well, if we take the limit as n goes to infinity of the Riemann sum, that is the area. How do we know that's the area? Because that's the definition of the word area. The definition of the word area is that procedure, which means the definition of the word area is the limit of a Riemann sum, but the limit of a Riemann sum is the definite integral. And so the reason the area is equal to these things is because that's what the calculus requires. As it turns out, all the familiar formulas come from that. But that's where area comes from. And every time you compute one of these definite integrals, one of the potential interpretations is area. There are other interpretations for definite integrals, and that's where other formulas come from. Formulas you get in physics, formulas you get in chemistry, formulas you get in the natural sciences. But all of those come from the calculus. Each of those is true because that's the definition of those terms. And so that's the relationship of area to Riemann sums to definite integrals, and definite integrals to this computation with the fundamental theorem.